Okay, hey everyone. So welcome to my stream. This is the fourth episode, and today we're going to talk about DEF CON CTF, which happened in Las Vegas basically last week. So I'm going to actually chat about a couple of things. I'm going to, first tell you what's DEF CON CTF and why everyone's so excited about it. Also, why was it special this year? I'm going to chat a little about how did it go for my team, and then I'll show you a task or three and how to exploit them. So it's going to be partly talking, partly technical, and yeah. So actually the stream was, I did post a link on both NetSec and on Reddit and in a couple of other places. So first, let me maybe tell you, the new viewers who are first time here. Who am I? I'm Genvail Coldwind. I'm the captain of Dragon Sector. So Dragon Sector is actually a CTF team. And let me maybe move myself here. We have, 13, 14 people right now. We're a team from Poland. We compete in Capture the Flag competitions for 3 years, 4 years, something like that now. And the CTF time ranking, if you care about that stuff, we're actually in somewhere around top 2 usually. 1 year we're top 1 year we're top 3, you know how it goes. But we're somewhere there. Apart from that, I'm daily, I work at Google. I'm an information security engineer and manager actually for a couple of years now, and I do security research daily basically, mostly around fuzzing stuff. So yes, so my team also went to Vegas, and that's why I'm going to talk about it. Now, before I begin, I would like to thank the usual people, meaning KrzaQ, which is, this is how you read this actually. KrzaQ is going to be my moderator today, so thank you for being here. He's going, if you have any questions either on IRC or on YouTube chat, then just say hi to him and he will pass the message to me. I actually hear him on a voice chat. So I'm not going to watch the chat, but he is, so message him. Apart from that, I would like to, as usual, thank Nervous Test Pilot for, allowing me to use his great music during my streams. Okay, so I did said that. Now let's get going. Before I get to DEF CON, if you're into security research, just before DEF CON there was the Pony Award ceremony giveaway. So Pony Award, if you're new to security, is basically kinda Oscars of security. Sometimes we like to call them that. It's basically one of the only awards in offensive security and security research out there. Usually there are nominations somewhere around July, maybe June, and then a committee of known professionals selects, winners. So yeah, so this year there was like a Match, for example, got a Lifetime Achievement Award, and this is a pony he got. Our people got ponies like this. For example, Tavis or Monody got one, Ferman Serna got one as well, a couple of our people. You can go to ponies.com actually website and read all about the winners and all the cool stuff they did. Also be sure to look at the nominations as well, because there is some crazy good stuff here. As every year. So from our CTF team, actually, Mateusz Jurczyk was nominated for his font research. Mateusz actually already has 3 ponies in different categories, and this is also his 3rd nomination, so that's quite crazy. Also, Robert Święcki, which is Jagger from Dragon Sector, also got nominated, but neither Mateusz nor Robert won this year. But they still did a crazy good research on this stuff. So be sure to take a look. Okay, so that was it. Now, about DEF CON. So let's start with DEF CON CTF itself. So what's so special about DEF CON CTF that actually is it's the main topic of CTF players during these months of the year. So first of all, is probably one of the only CTFs at this time, but apart from that, it's not about the prizes actually. There are some Korean CTFs where you can win 40 or 50k in dollars for the first place, but this is not one of them. It's actually special for a different reason. So first of all, it's super hard to qualify for it. Actually, if we go to, I guess it's legit BS CTF site, you can see how you could qualify to it. This is the official. It's actually super awesome. I love how this website is made. It totally looks like a legitimate business syndicate, doesn't it? Anyway, so to qualify for DEF CON, you should have won either the last DEF CON, which DEF CON did, and they got qualified from this, or a couple of other major CTFs during the year, for example, HitCon, Rus CTF, 32C3, which is CCC CTF, which is actually at the end of the year, is like the finals of the season usually. Boston Key Party or played CTF, and they also run the qualifiers, which we did qualify from. The qualifiers were actually super hard this year, as in the competition was just amazing, and the tasks themselves were really crazy. There was, for example, one Windows hip exploitation task, which took Mateusz and me in the end also, I don't know, like 45 hours total, being 40 hours of his work and 5 hours of my shellcoding work. So the tasks were crazy, but we managed to qualify from the bottom of the pool actually, but yeah. So we qualified, and then after you qualify, you go to Vegas to DEF CON basically. And all the 3 days of DEF CON there is the competition, so you don't get to see the conference. I was like 3 times on the finals already, and I think I saw half of a talk on DEF CON, and that's about it. So you don't go to DEF CON really, you go to DEF CON CTF. Anyway, so basically the special thing is that it's really prestigious, it's really hard to qualify for it, and in the end, as you can see, about like 15 teams make it. Now, usually the qualifiers are Jeopardy style. So, you get tasks and you have to solve them. However, the finals are always attack-defense style, which is a little more funny because, first of all, it's more demanding on the teams. You have to have basically your eyes around all the time to be able to both defend, find vulnerabilities, and patch stuff. Now, this year's was also a little different attack-defense scenario because, like, both previous years and 2 years ago, during attack defense, it was like a normal attack defense. Like each team had a server, they had some vulnerable services there, and you had to find vulnerabilities and patch it there. However, this year it was the DARPA cyber grand challenge thing, which is so if you don't know some context here, so CGC was actually a competition for US organizations. I think only United States organizations could attend, so, well, there were a few Europeans there, but, well, playing as part of other organizations, I guess, from the US. Anyway, the idea was to construct automated systems for detecting vulnerabilities, patching vulnerabilities, and exploiting vulnerabilities. So you basically created like a CTF bot, I would say, for like exploitation purposes. And the bot was supposed to, well, be useful for a platform which is called Decree. And the Decree is actually x86 Linux, but it has a different syscall table, and the syscall table is actually like this. There are, well, not really a lot of syscalls, as you can see here. Yeah, these are all the syscalls. So usually, on Linux you have, 300 syscalls different, right? Now, that's not true for Decree. On Decree you have 7. You have terminate, which is, just exits. You have transmit, which is actually send, write, something like that. Then you have receive, which is obvious, is read or receive. FD-wait, which is select, basically. Allocate, which is mmap, and deallocate, which is unmap. And, or umap, whatever that syscall is called. And then there's random, which basically gives you pseudo-random data, which it's like, I wanted to say it's from dev random, but that's not actually true. It's seeded, so it's random, but in a cryptographical safe way, or it's supposed to be, but it's still seeded, and the seed is archived for Why is it archived? It's archived because the platform itself is supposed to be fully deterministic. And what that means is, it means that if you get an exploit and you get a challenge and you like run one against the other, and you have a given seed and you recorded it, and when you replay it after some time, it's supposed to behave in exactly the same way. There's supposed to be no randomness when replaying it, but you do have random for actual randomness during the competition. So that's one interesting thing about it. Now, another interesting thing is that this platform is actually, it is x86 Intel, so it's complex in terms of machine language, and there are like all sorts of usual vulnerabilities, but there's no ASLR, no ASLR at all. So the stack is always in the same place, the heap is always in the same place, the images are always in the same place. There's no ASLR whatsoever, so that also simplifies things a lot during exploitation, right? That's not the only thing which is different. So the machines weren't supposed to do a full weaponized exploits as you do on CTFs. So on CTFs, what you do is you find the vulnerability, right? Then you write an a partial exploit which actually triggers the vulnerability and gets you controlled EIP. And the third thing you do is you actually write a shellcode which spawns a shell or reads a flag or does whatever. And so you get access to the machine or the flag which is remotely hosted, right? Now this isn't the case for CGC, and it wasn't the case for DEF CON this year, which is quite surprising, because what you had to do is, instead of full exploits, you had to do so-called POVs. A POV was that was proof of vulnerability. As in, it was an exploit which stopped at the second stage. So you had to find the vulnerability and then you had to trigger it. You didn't really have to trigger it as in get controlled EIP and another register or leak some data, but which I get to in the moment. But in the end, you didn't have to do all the shell coding thing, all the exploitation thing, which made it easier. It made it actually easier in comparison to, for example, the challenges on the Jeopardy style qualifications. Now, as I mentioned, for example, in the quals, there was this Windows task with heap exploitation, and we spent 5 hours on shellcoding, right? So if you don't have to spend 5 hours on shellcoding, then you actually, it's way easier to, to finish. You finish the task earlier. So this is one thing. Another thing is that actually the machines were also supposed to be able to patch the CGC binaries, and we also had to do it on DEF CON since that was an attack defense. You usually have to patch it as well. Now, why was DEF CON CGC this year? This is a good question, and the answer to this question is quite interesting. So DARPA actually, during the DARPA competition, I think the competition, please correct me if I'm wrong, but it was like around 2 years or 1.5 years, and at the end, like the best bots which qualified, just a day before the DEF CON CTF, the bots competed against each other, and one team won $2 million, if I'm not mistaken, for being creating the best exploitation bot. And what the organizers wanted is they wanted for the machine called Mayhem, because Mayhem actually won. They wanted Mayhem to compete in DEF CON. Therefore, the format of DEF CON had to be the same as the format of the DARPA CGC competition, which means humans had to learn CGC and not the other way around. Now, Mayhem was created by For All Secure. Now, before I go further, I would like to point you to 2 links. I put them already in the description of the live stream, but in case you missed it, I'm going to paste them both on YouTube channel and on IRC. So, one is an article by a PPP member, by Zachary Wade, who, they won this year. Spoiler alert, they won DEF CON. And this is, you might want to read it, because this is like perspective on the whole thing, which I did mention from the winning team, from their perspective. And another thing which you probably want to read is how the machine competed, and there is a case study about one of the challenges. The challenges had names like this, so there were usually a number and like some identifier. You might want to read this as well. This is actually cool stuff on both fronts. So I wanted to be sure to post these links here. Okay, so yeah. Anyway, so one thing which is pretty awesome is that at least one person, Vito, from the organizers of DEF CON, is on IRC channel and I think on YouTube chat as well, so he will be able to correct me on the things I get wrong in what I'm saying. Anyway, so yeah, so DEF CON was DARPA CGC this year, and that was, in all honesty, that was one of the reasons we were thinking really hard if we should be going to DEF CON finals at all. Because first of all, we have to think from a perspective of a team who plays a lot of CTFs and who travels a lot, and we don't have sponsors, so we do have some travel budget which is rather limited. On DEF CON, even if you win DEF CON, you don't get prize money, which could, for example, be used to buy tickets for airplanes and some such stuff, because they want money for that, it seems. So you do get black badges, which is pretty awesome, right? Because you are able to attend DEF CON, every future DEF CON conference for free, basically. Anyway, so we were thinking if we should actually go, because, CGC is kind of a toy platform in comparison to real x86, but there are a lot of common points. Now, we don't really deal with in our daily work with CGC, right? We deal with x86. Now, one could say that this is the same case for all the teams. That being said, that's not true, because at least, 2 or 3 PPP members, and I know some Shellfish members as well, did compete in DARPA CGC. So they did get to play with this platform for the last 2 years with the format of the competition, so they had there was an obvious bias in that direction. But in the end, we decided, it's like an experimental year. We'll get to compete against a machine. It might be fun in the end, so let's try it. When we actually saw the POV XMLs on the qualifiers, we weren't so happy about the decision, but it turned out that the XMLs are optional, and we did not using them. I'll show you POV XMLs later on. Anyway, so we decided to go. Now, one of the things you do on such competitions, you usually need to have a really good cyber server. Actually, the cyber tape was from Eat Sleep Pwn Repeat team, which borrowed it to us. And yeah, we had a server which was able to run CGC, and we could therefore do all the debugging, all the stuff on that, or on provided VMs from the DARPA competition. Now, so how did it go? One thing before I forget, actually DEF CON badges this year were really cool. They looked like this. Maybe let's switch here. Yeah, so it's like Attack on Titan SQ badge, which, there are buttons, and it actually lights up the eyes sometimes, and you can probably do really cool stuff with it. I actually have no idea what to do with it yet, but there are some interesting things which maybe you can connect to at the end. So the DEF CON badge this year was really, really awesome, in my opinion. It's said to be like x86, by the way. I have no idea if that's true, but I don't know. I'll check it. So, in comparison, actually 1 year ago, the badge was like this. The badge was, it's a vinyl, disc. As you can see, there is some tracks here, and there probably were some cool challenges where I didn't look it up later. And 2 years ago, it was also like this, pretty cool, like an electronic badge as well. So DEF CON badges are really cool. Actually, I saw only one conference, which was like a super small university made conference on, I think it was university made, maybe not. Conference in Poland. They also had these which you could connect to basically your laptop. Yeah, so while I'm showing badges, I also got this badge from a couple of people on from the Grey Hat, which is a special interest group from Korea. Singapore, I think Singapore. Sorry about that. I got this badge, which is really awesome. I'm going to probably play with it later on some streams. Yeah, so Vito says that like the vinyl record was like the biggest DEF CON batch ever, and yes, it was a record. That's a nice pun. Okay. Anyway, so there's a comment that there was another write-up which was from about CGC, but Michał says he cannot paste the link. So Michał, if you go to IRC, you can actually paste links there, because I know that YouTube chat does not allow link pasting. I'm sorry for that. I have no idea what to do to disable that anti-spam filter, because I would actually welcome links on the channel, because I know there are like a lot of okay, KrzaQ says that I should give him I should give him privileges to paste the link, and he will paste it. So he'll paste the link around for the another write-up which Michał mentioned. Sweet. So back to business. Okay, so each team had a basically table like that. There were places for 8 people at each table, though more additional people could play from hotel rooms or whatnot. We had like one person playing from the hotel room. Usually it was me. And apart from that, we had, I think, 2 or 3 players remotely who tried to fight with CGC as well, which was pretty cool. Thanks for joining. And yeah, as I said, there were like 15 of these tables all around, one occupied with a machine. Basically, I don't know if machine needed 8 places. It was rather small in comparison, but yeah. Apart from that, there was the scoreboard. Now, the scoreboard, well, actually it wasn't a scoreboard, it was a visualization. As you can see, I tried to make a photo of it, but I have absolutely no idea how was it displayed by the projector, but my camera couldn't make heads or tails of it. So let's assume this is it, but it was actually it was actually blue. And all of these, like this is a circuit, as you can see, all of these were actually representing the teams, and you could see some stuff moving around. Probably that was like who got points for owning who. Now, apart from that, do I have any cool photos? No, I think that was all the photos I made. I forgot my tripod and it was really dark in the room, so not a lot of photos this year. So yeah, apart from that, after we got there, there was a slight delay in starting the competition. I think it started after a couple of hours, but we didn't mind at all because we still had like tools to finish. Since we treated this as an basically experimental CTF, we didn't put any, too much effort. Actually, did put some, but we didn't put too much effort into preparing tools beforehand. So we had still some finishing up to do. And some people were still like looking on, oh, what is this CGC stuff? It was good, but it was x86. Otherwise, it might be problematic. So after it started, then you got a binary, and apart from the binary, which you could reverse engineer and you could create a POV. I'll talk about POVs in a second. You had to also patch it. Now the patches were actually public, which means that you could see how the other teams patched their server. You could actually swipe the patch from them and apply it in your binary, which is the reason why we were actually like top 15 in the on whole Saturday. But I'll get to that. So that was actually pretty cool, because what you could do is you could analyze the patches and see, hey, maybe these guys like had a problem in their patch. Maybe we can still exploit them. That turned out to be true. In some cases, like in the 3rd day, and I believe also the 2nd day, Robert, which is basically was our fuzzing specialist, fuzzed a lot of teams' patches, and it turned out that like some teams did not patch correctly, and we still were able to create modified POVs and own them up up until the end of a competition, basically. So that was, I really liked that aspect of it, that the patches are public, that we can analyze them, we can do patch diffing, we can compare it, we can see if like everyone got it correctly. So that was cool. Now the other part of this patch metagame was that, hey, if a team actually, swipes a patch from us, maybe we should backdoor it. Now, we chatted about backdooring our patches. In the end, we didn't really have time to do it, but we chatted like, but if it's a backdoor, like send a signature, and after sending the signature, you get the type 1 or type 2 POVs like just handed to you. That's not a great thing, because the signature, like any team can replay a signature, and that's bad. So you'd have to use probably some public key cryptography here. Now, we didn't do it, but PPP did it, like the winners. That was unfortunate, and they did it only on Saturday. So what happened was that during the whole Friday, we swiped a couple of patches. We were mainly like borrowing patches from other teams, because our patching system didn't like CGC binaries. There was some slight difference between, so CGC binaries are an ELF basically, but the linker created it in some kind of weird way that our patching system didn't really like. And we tried to fix our patching system, Friday, Saturday, and we still didn't get it correct on Sunday, if I remember correctly. So we were relying on either, hex editor patching, the old school way, or we were relying on other teams' challenges. Now, all Friday, we did reverse engineer every single patch we took, and we checked, hey, is there a backdoor here? No? Okay, let's apply it. And, also merging patches, as in like, oh, this team actually fixes these bugs, and the other team fixes like another bug, so let's just try to merge them. One thing here is that to note that each challenge actually had a couple of bugs. It wasn't like, well, I think there was one challenge which had only one bug, but apart from that, like, there were multiple bugs in each challenge. So yeah, in the end, you had to patch a couple of times. Now, on Saturday, we were like, we knew that our patching system is broken. We are losing SLA, which is basically our challenge was not stable, was not able to respond correctly to the tests of organizers, because the organizers were testing if you didn't, overpatch it, like change the binary, so it's like it just says hello world or whatnot. So we were testing if the binary still behaves correctly in the if the service is still doing what it was supposed to be doing. Yeah, and we are losing SLA because our patching system was not working. Therefore, we decided to, hey, we need patches right now, and we just stole them from PPP. And it turned out that on Saturday they decided to backdoor their patches. So the whole Saturday we basically were losing a lot of points just because PPP was, we didn't notice the PPP backdoor up until the end. And in the end, we I think Redford finally analyzed the patch. We were like, we knew already there was probably a backdoor there, and he found the receive function being hooked, and I think it was like a type 2 POV, which I'm going to discuss in a second. What was that exactly? A backdoor which leaked some, like a given piece of memory, encrypted it with public key of PPP, and then just like when their POV did receive it and decrypted it and submitted it as a flag, right? Yeah, so that was PPP. That was well played. I was actually like jokingly suggesting a drinking game to do today. Every time I say like a bad word and then backdoor, you should drink, but I'm probably not going to swear a lot. So sorry about that. Anyway, the move with patching on Saturday was great. I actually heard two theories or hypotheses on why they started Saturday. So first was because they thought like, okay, people will check on Friday, so let's start it Saturday. If that was the case, that was a great decision. Well done. And the other thing I've heard was that actually the person who was responsible for backdooring was late on Friday, and he only got the backdoors running on Saturday. In either case, not seeing any backdoors on Friday did kind of influence our decision to use your patches. So well played. That was a cool meta game, and it actually, I think that's the reason why PPP won in the end, because they got a lot of points from the backdoors. Apart from exploits, of course, and exploiting everyone, but if the patches are public, then people usually patch themselves really quickly, unless they scrub the patch, of course. Okay, so there's supposed to be okay, there's the question, how did we compare the binary patches? So there were two ways to do it. One way is to use something like bindiff or patchdiff for IDA. So, as you know, it's basically an extension for IDA, which tries to match all the functions, and when it matches the functions, it tries to tell you that well, this function is matched, as in it's probably the same function, but hey, there's like a change in this area, right? So that's one way. I did try it, but I didn't use it in the end. What I did was I did simple binary diffing of both things, and I had in IDA opened like both files, both version like unpatched and the patch which I was analyzing. And I looked at the offset of the file where the difference was found, and then I looked in IDA in these places. Now, I did it because it turns out that bindiff and so the tools don't really take into account that, hey, this is actually the same binary, this is the same version of a binary, and it was probably, like in place patched, and it's not a new compilation of a binary. These tools were created for, for like version 1 of the software, which is then recompiled, and there's the version 1.1, which has all the functions in different places. Now, in case of patches, all the functions were in the same place, but the tool didn't take it into account, and there were like a lot of false positive or a lot of mismatches. So in the end, I decided to just do bindiffs, like binary diffing manually, and look up in IDA what the change was, and that turned out to be more effective in my case. But like everyone has its own preference as far as these things go. Yeah, so apart from that, let me think. So yeah, these were the patches. Apart from patches, you also got network traffic, and network traffic, it was like standard on attack. Well, maybe not standard, but on DEF CON like last year and 2 years ago, it was that you did get pickups, I believe, from the traffic from a given round. Here you did get just the files, which, well, so I don't remember exactly because I am not the person who actually did it, but you did get the traffic, which looked, for example, like this, and if you put enough effort, you could actually create a system which would grab the POV traffic, the exploit traffic from these files, and replay it to other teams. And I know that some teams, for example PPP, did create systems to do it. I believe we didn't do it, but we did use these for... Maybe we replayed 1 or 2. We didn't have an automated system to do that, but we did use, I think, the input from these pickups to fuzz some targets, which did score us some POVs, basically exploits. So that was cool. You actually got quite a lot of things. I think I have like 25 gigabytes, of course, of traffic on my hard drive. So that's quite a lot. And thanks to Sergush, who actually did send me these, because I didn't have it on my machine because I was not dealing with it during the CTF. So that is that. You had the patches, then you had the pickups, then you had one more thing, which was what's it called? IDS. You had basically a firewall which you could set some rules. I actually didn't play with that as well, but what I've heard after the competition was that if you had a firewall rule set, then it was really slowing down your system, and there was supposed to be some scoring, negative scoring around low performing demons, right? Services or challenges, whatever you call them. So we didn't end up using any of that. We did just rely on patches. We did have some ideas for metagame after that, because the firewall rules were supposed to be programmable. I think they were like maybe CGC binaries. I'm not sure about that, but that's my guess, right? And so what we thought of doing was having a hooked, basically having a firewall rule which was flip some bytes, and then a hooked receive function which would also hook, would also flip the bytes in the same order. So if anyone would stall our patch and they didn't steal the IDS rule, then they would actually have a worthless patch which would fail on SLA, so they wouldn't get any points for having the service up and running, because it wouldn't be replying correctly to whatever the organizers were testing them with. Yeah. So that's that. And I think these were like all the three things. You actually had an interface for it. I do have some screenshots, I believe, for the interface. Let me just quickly look them up. Now, where do I have them? That's a good question. Oh, here. Okay, so the interface looked like this. You had the challenges, right? There were like some information on firewall. You could click basically everything, and you could like click firewall details, and it would get you to the details. You could get details on the round. You could basically go to another section where there were all the information about which. I think I also have a screenshot of that. No. Yeah, you could go to the section where there are like binary replacements which you could make. You can list all the patches from different teams which were applied. So the patch was actually a patched binary. It wasn't a patch itself, right? And you could also see if your POVs are actually POVs which you executed against a given team in a given round, whether they hit or not. So for example, you can see, I think this was from almost the end of the competition, we were still hitting some teams with some POVs. Now, I didn't mention it, but it's if you played Attack Defense CTF, you probably know that the game is divided into rounds, and each round is basically like 5 minutes. I think on this year's DEF CON CTF it was from 5 minutes to 13 minutes, depending on which time of the day we were, because there were like some heavy processing in the background and it was a little lagging during the day, so the round times were growing. In the end, you either get a score during a round or you don't. There are some more complicated issues related to scoring, which I'm not really super familiar with. But due to how scoring worked, basically due to the backdoor which we used and didn't check for, which was totally our bad, we went Saturday basically to top 15, and until we removed the backdoors. When we removed the backdoors, got some new exploits in place, we even like just last round of Saturday we basically jumped a place up. So we probably did a little better on Sunday though. So yeah, but in the end we finished, our team finished like somewhere down there, right? Like after top 10. So that was how DEF CON worked basically. Apart from the delay, it actually worked pretty smoothly, I would say, at least for the people. Now the machine is said to have some bigger issues. There were some, I don't know, interface problems for the machine, so it was not able to fully reliably play with full power, if I understand correctly. I don't have details on what exactly was wrong. There will be... I'm actually looking forward to a post from the Mayhem guys. Maybe they can, or the Legit BS guys, they can maybe explain what did fail, what was correct, and we can read about it. I'm not sure if the machine would do super great in the CTF. It's something, but a question which remains unanswered for now, I guess. Cool. So I guess I'm going to make a break in a couple of minutes, in 5 minutes, but and after the break we get technical, and I'm going to show you a couple of challenges. Well, actually, I'm going to show you probably one challenge, but 3 bugs in it. So yeah. But before I go there, I'm going to show you the CGC platform. Okay, so my patties actually has a super small font. Let me maybe span a Linux console and connect to it. So the platform was basically distributed as a vagrant, I don't know how you call it, container or whatnot. I extracted it and I'm just using it with plain vanilla VirtualBox. So yes, let's do it like this. I actually have a password set here, which I totally don't mind if it leaks, so I'm not turning off my mic as I usually do when I'm typing a password. Okay, so yes, XMLs. So we do have an XML here. This is what we like first saw during the qualifiers, and we're like, oh my god, an exploit in XML, are you kidding me? Now, this is actually, when you start reading it, is actually a list of events which are supposed to either happen or a list of actions which you initiate as a POV. Now, a POV is think of it as an exploit binary. So you have, like, a service, then you have a POV, and they chat with each other on like a network, which is basically standard input, standard output. So these are just like two binaries chatting with each other. Now, as I mentioned, POVs had two types. There was type 1 and type 2. So the creator of POV selected the type of a POV, and the POV type was the what do you want to prove? How do you want to prove that you actually do have a vulnerability and you have a control over the process, right? Type 1 was basically you had to get two things. You had to get control of EIP, so yeah, like for one or whatnot, and you had to get control of another register. But you could select the register you wanted, but you had to have control of EIP and your register, and you also could select actually a mask for these things. So you didn't have to control all the bits, but you had to control at least, I think, 20 bits of each EIP and a selected register. So for the register, you also were able to select which register do you want to control, right? So 2 is, I don't remember, like ECX or whatnot. Yeah, so it seems that Mayhem was not able to get the network traffic from all the exploits going at it during 2 days of DEF CON competition, because the client and server were swapped in comparison to what the machine actually expected. So yeah, that's probably did handicap it a little, well, maybe a lot. So that's unfortunate, but it happens, right? Okay, so this is type 1. Again, one register, fully controlled, 20 bits at least. You can fully control it, obviously, and EIP. Now, type 2 was actually different. Type 2 was you were supposed to leak data, and you were getting from the, because this is negotiation, right? So you're getting from the judge binary, let's call it like that, area, the address of memory which you're supposed to leak, and the size of the data you are supposed to leak. And that's it. You are supposed to leak that part of data and send it to the judge to get the points. So that was basically the flag in that case. Now, the negotiation in this case, in type 1 case, you actually got, since you were able to select both the register and the mask, the judge binary was supposed to select the value for the EIP register and for the register. So you had to have at least like these many 20 bits or like all the bits set to these registers with accordance to what the judge binary told you to set it. So if we get technical, the negotiation was actually like on file descriptor 3, and it has a really simple format I'm going to show you in a second. Anyway, so back to this. So first thing for POV was that it was supposed to negotiate the type of POV with the judge binary, or whatever it was called officially. And then there was a set of actions or events. So for example, delay was, delay 10 milliseconds, then read until echo service is spotted in the data stream. So yeah, this is like waiting for an event. And then there is an action which is write, and it writes some data, ABC, which is just ABC like 41, 42, 43, if you're into hexadecimal. And then this is actually a variable type 1 IP, which is the value, the exact value you received from the judge binary, well, POV received from the judge binary is placed here in little endian 32-bit format. Same here with the register value, and then there is more data, which is just, this is unescaped, so this is like the end of a line. And this is written to it, and that's basically it. There is, as you can see, no like complex interactions in XML. I'm not sure if that was possible. So the first time we saw it, we were like, okay, how do you make a complex exploit in XML? We don't want to do it, we don't like XML. What it turned out that you actually don't submit the XML, you do a POV-XML to C, and you compile it. And you get a nice C code generated out of it, and you can actually see, negotiate type 1, all the parameters you gave it, then delay, then read until something, this is the delimiter, there are a set of functions in libpov. So that was already better because we could code all our exploits in C, which isn't great because, you don't usually code exploits in C, that's the old school of doing it, but what you still do for privilege escalations bugs and so on, for kernel bugs, right? But for remote exploits, you usually do use Python or something like that, like Ruby. And so there was a team before the competition, they said like, hey, we are actually porting MicroPython for the CGC binary, for the CGC platform, and our POVs are going to use MicroPython. I think they actually shared it, and we did decide to use it as well, so we did use MicroPython in the end instead, and we've written our exploits in MicroPython. I know that PPP used Python, like not MicroPython, but just Python, so their exploits were in Python, which turned out to be way better because MicroPython is weird in some cases. It's not fully compatible with Python in terms of grammar, I would say, or things you can do in the language, because I ran into some problems, and I guess some of the guys did in my team as well. But it was still way better than writing the exploits in C. So yeah, anyway, if you get the C, then you had to compile it to a binary. Let's just do this. And there was actually on the image, there was provided a compiler for CGC, which you run like this. I'm going to copy-paste a huge line, which is C-lang for the CGC platform. Again, CGC was basically ELF, but with a different beginning of a binary. But this is actually not needed. This is about warnings. I have no idea what unpatched means. There is no standard library, no built-in functions, and so on, but it actually does use... it will complain about it? No, it doesn't, but it does use, libpov thing. And after you compile it, you can just link it again for CGC platform, and what you get if you do file, and it's called X, I believe, it's a CGC 32-bit binary, which again is like basically ELF. Yeah, so if you run it, then if you actually, as I said on the file descriptor 3, I think actually zoom it now. Yeah, let's do like this. On file descriptor 3, if you let's redirect it to 1 to standard output, there is the negotiations going on. So if you do hexdump-c, you actually see, well, you can see the packets here, right? Okay, this didn't work out as I intended to. Let's do it like this. Yeah. Okay. So this is the negotiation, like type 1. Like you're negotiating type 1, so that's like 4 bytes. Then this is like the EIP mask, is a little endian, of course, is exactly the same thing which was in XML. And then you negotiate the mask for the register, and then you tell it which register number it is, so it was the second register, again, little endian. Now, this exploit doesn't do anything in this case because the server, like the judge binary, was supposed to reply here with 2 D words, saying what the value is supposed to be. So if I would actually put some values here, it would work. We can actually try it out. Let's do like this. Let's do cat. No, sorry. Let's do echo AAA BBB. I think that should be enough. And let's move this to the third descriptor, and this should actually more or less work. No, let's put it in a file. Let's go to LLL. And here the third descriptor is supposed to come from the file LLL. Yeah, so it, delays now. I think it delays. We can actually use strace. Oh no, it waits to receive some data, and the data was what was it supposed to have? Let's look at the XML again. Echo service, right? So echo service. Yeah, and it replied with what was it supposed to reply, right? So AABB is from the server is the this part, and then there's the new line sign, basically, which is correct, and ABC at the beginning. So this is how POVs worked, and they chatted with the binary on standard input, standard output, so there's like no magic here at all. Usually, of course, I learned it on the third day on the competition, and before that I treated it as a black box of some kind of the negotiation being totally magic, but yeah, on I think the evening of the second day, there was a challenge released with 4 binaries chatting with each other, like IPC, right? And to actually be able to run it and debug it, we had to modify our tooling, and this is the moment where I needed to get into like how does it actually work. Yes, so okay, so let's make a break for 7 minutes, and after 7 minutes I'm going to have some music in the background, and after 7 minutes let's get back and I'm going to show you an exploit or two for the binaries, for one of the challenges from DEF CON. So thank you for being here, and see you in 7 minutes. I guess I'm going to leave you with some music. Okay. Okay, so I'm back, but you cannot see me yet. Now you should be able to see me. Okay, so you should be able to go, but you should still hear the music. Now there should be no music, and you should be able to see me, and I think we can get going. So, one question which was on chat, which was really interesting, is can anyone recommend any other YouTubers, basically, or streamers which talk about security? Which is a good question. I actually have absolutely no idea where is this. But there is this securitytube.net thing, which I think there are a lot of videos about security there. Yeah. I think these are like mostly embedded YouTube videos, but maybe something changed. Anyway, so yeah, SecurityTube, they have a really good collection. I'm not sure about like what level of things are there, like if you have to be like a super pro to understand it, or if this is beginner stuff. I have no idea, but yeah. If you do know anything else, please tell us on chat. On IRC you can paste links, actually on YouTube chat you cannot, or in the comments below the video if you are watching after the live stream, obviously. So let's exploit stuff. Okay, how to do it? We're going to play with a binary. I just need to find it. Is this it? Yes, it is it. Okay, so this is a binary we got on, I believe, the second day, was it, or the evening of the first day? Oh, wow, Tavis, hey Tavis. And okay, so the binary was actually rather huge-ish. You could like scroll through it, and there's like a lot of code. Let me show you it a little. What was the start symbol called? Oh, okay. And I'm going to actually do this. Yeah, and this was the main function of the binary. You can already see some strings here, which is quite good always if it's not binary stuff. And if you scroll down, you can see it's actually like a lot of cases. So this was the binary which I was playing of, well, mostly during the CTF. It was legit 0007. And if you run it, you actually get this. 7. Yeah. You can type something and it tells you undefined. So it's probably either a shell type of binary, or maybe it is, I don't know, an interpreter of some language. So how you approach this binary at a binary like this, usually on a CTF, you start playing with it, you start putting in different stuff, right? And it behaves differently when you put various stuff, so you get to know more of what probably is it about. We discovered a couple of things. We discovered, for example, that if you type in integer, it will tell you it's an int and the value of it, so it's probably already an interpreter. If you do like this, it actually gives you the result, so it's maybe a calculator of some kind, but it also seems to support strings, but though in a little different way. It doesn't say it's a string. Then we found some string references here, for example, where was it? Let me scroll up. Like expand tab, swap cases, lower or upper, right? So we decided, hey, let's try maybe asdf.upper and see what happens. Let's try it like that. It didn't work though, right? So then we figured maybe there's like, some value assignment. Maybe we can do a equals 1, 2, 3, 4. That didn't work either. Somebody then thought, hey, maybe it's like Turbo Pascal thing. So it's like colon equals. And sorry, let me maybe do this. Yeah. And this turned out to be actually a good guess, and we knew now that there were variables there. Now the problem was that there was no multi-assignment, which is good, I guess, but you couldn't assign the same variable twice. And now if we would actually try the upper thing again, but this time to put the string into a variable. If we do b, then the string is evaluated. So if we do this, oh, this doesn't do anything. It does, no, sorry, it changes it in place. So as you can see now, if I type b, it gives me this. yeah, so basically this is what we guessed at one point or the other. We didn't find any functions which, you know, are usual in this kind of things, but that was something. Now, we were also not sure about this switch here. It was a huge switch, and I actually called it state, but it was switching from state, and there were a lot of cases. I'm still not sure what these are. I don't know. We found a couple of vulnerabilities, we exploited them. I have still no idea what these are. It wasn't important, it seems. Now, so the first bug, we actually spotted it really fast. I'm curious to see when there will be, you know, full results with full the data of the competitions, then maybe you can see if we got first blood on it, but we were rather quick with spotting the first bug. So looking at these strings, what I found was expand tab. Now expand tab, what it does what the name says. It basically changes tabs to usually 8 spaces, right? Now the problem is if you miscalculate the buffer length of the destination buffer. So if you have actually the string of size 2 and both characters in the string are actually tabs, then if you expand it, you need a buffer of 16, assuming that tab is 8 characters. It wasn't the case here, but yeah. But if you have a destination buffer equals to the size of a initial buffer, then you get an overflow of 14 bytes. So that was what I was expecting here. It turned out that there was a vulnerability here, but it was a different kind of vulnerability, which I'm going to show you. So this is it. This is like super simple code, basically, as converted. So in a loop, it looks for tabs, and it changes the tabs to, this is also, a character. It changes this to 3 spaces. Now the destination buffer, so this is actually somewhere here. It's actually seems to be on the stack. So if it's on the stack, then, and the stack, as you can see, the buffer size it's probably like 256, but IDA, as the compiler, for some reason, for optimization reasons, probably thought it was a little smaller, but it's 256 buffer on the stack. And you can see there are like, there is no boundary check here. This check is actually against the size of the input string. It doesn't check if the output, if you put more data there than 256. So this is a buffer overflow, like a stack buffer overflow if you put whatever amount of data there, which exceeds this value. So that was the first bug we spotted, and we exploited it rather quickly. Let me show if we can trigger it actually. And I'm going to actually copy paste quite a lot of base here. Yeah, this should be way above 256 now. And let's do expand tab on it. And it crashed, as expected. So that was the first bug we spotted. It wasn't the exact bug I expected, but it was there. So exploitation of it is rather simple. So let me do something like this. I'm actually going to move away my GDB init script for now, because it will be useful in another exploit, but not yet. Let me call it like just GDB init. I'm going to run it. You can actually debug the CGC binaries in GDB without a problem. So we actually provided the modified GDB, which was awesome, the DARPA guys. And it was called org for being the original binary. So yeah, so let's run it. And I'm going to again set it for a huge value. And expand tab. And as you can see already, the EIP is like for 1, for 1, for 1, for 1. And there were no stack cookies either in this compilation. So if you look at the registers, we could also control EBP. So that means that we already have type 1 possibility of creating a type 1 POV. So what we had to do in the end is, is just put a lot of A's, figure out in what place there are actually the value which is placed in the EBP and the value which is placed in the EIP. And that's about it. So one hint here, if you're well, this is a basic stack-based buffer overflow, like the basic as you get. It's the simplest as you get, nothing simpler ver than a stack-based buffer overflow, which just overwrites things with data. But in case you're new to all this business with exploitation, I'm actually going to show you a quick hint on how you do it in a fast way that you find in which place in your buffer you actually do overwrite some stuff. So what I usually do, let's make it, how do I get out of this mode? Sorry, I'm new to the tool which actually does the zooming and the drawing on the screen. It's actually a tool from sysinternals from Microsoft. Super small tool, really useful. So let's create aaa.py. Okay, so what I usually do is I create a buffer with which has the padding, right? I know there will be 256 bytes of A, and this is not going to overflow the buffer, but everything else is going to actually overflow it. So what I do add to it is something you can just distinguish, like values which you can distinguish, and for example, AAAA, BBBB, CCCC. I know that the values in the registers are 4 bytes, right? 32 bits. So that's why I'm using quadruple A, quadruple B, quadruple C, then D, E, F, G. Sorry, how many Fs do I have here? Yeah. And that's it. I'm going to just print it. I'm going to use this as a buffer. It should be already enough. So Python, yeah, I'm going to copy paste it, and I'm going to again run it in a debugger. Okay, and as you can already see, 4343 was in, that's C, letter C is in EBP, and letter D is in EIP, so in case of our exploits, what was left to be done was actually change, like cut it here, right? And then like do some DD, what was that, ABP first, so the reg value actually here. And DD EIP value here, yeah. And then like pack it and send it out. And by reg and EIP, I mean actually the negotiated values, so that we did get in our POVs from the judge binary. DD is actually like a super small function I really like to use. It looks like this. Which is basically like you give it a value. In this case, we assume the value is a number, and it packs it into a little endian 4-byte D word unsigned. But that's it. So if you look at my exploits, they're like, this function is probably everywhere. So okay, so that was the first bug we've spotted and we exploited. Now, before I get to the second bug, I'll actually jump to the third bug, which we discovered by patch diffing. I'm not sure if I actually have a patch at hand which led to the discovery of this. Let me quickly check it. I actually did have notes on, like during the CTF, I made notes on who is, which patch is, like what characteristics does it have. Maybe I will be able to show it, but you sadly need to give me a second. Okay. Okay, so I did find okay, so actually it was a patch from PPP that led us to the discovery of this, led me to the discovery of this bug. What's the number? 5A. Be so unfortunate if I would not have it. I really wanted to show you this patch. Okay, I do have it. Perfect. So this is the patched binary. And I'm going to compare it to the unpatched binary. Just need to find the right binary again. Yeah, okay. Okay, so this is basically like a Total Commander standard tool for doing binary diffing, which it's like meld basically on Linux somewhat, but it actually can display it hexadecimal. So I basically like went through all the differences between the binaries. So this is something I've mentioned, right? And I think this is like one difference that was really interesting. I kind of think this is it. I might be wrong. I'll get to the proper one in a sec anyway. So this is 440. So in either you can do jump to file offset, and need to do this 44A0. Yeah, and we get here, and there is I'm actually going to do in the original disassembly, I'm going to jump in the same place, and you can see that only difference here is that you have JBE here, and this is JLE. So one of this is jump if less or equal, and the other is jump if below or equal. And this is actually, yeah, so there is this check. And after this check is done, there is either something called, or if something is, or if this check is not met, then this is called, like out of bounds. Now, this check here is the patched version was unsigned, but the patched version, the unpatched version was signed. So as you can see, it was signed, right? Yeah, signed here. This is important. I actually didn't know what this case 70 is, but I figured it out quite quickly just by guessing, basically. And it's actually assignment by index. What I'm saying by assignment as, by index is actually this. If I run this binary again, the original one, then what you can do is, well, you can create a string again, right? But you can also change a given letter at a given position. For example, I can switch the at index 1 to x, and then, as you can see, well, this basically appeared, right? Like the x here. Now, what that check does is it checks for negative numbers. So, what happens if I do -1, right? Nothing happened. But did it overwrite the memory there? Yes, it did. So, oh, this was obviously my mistake. So as you can see, it doesn't crash easily. So I can yeah, put something else here, and it still doesn't crash. Now, to exploit this, you had to already know something about the variables and how they are constructed in memory. Now, the variables in memory are constructed like this. There are my notes here. You probably cannot read them because I have sometimes problems reading my own handwriting, and even if it was bigger than the small video screen you see there in the corner, then you probably still would not be able to read them. So I'm going to actually write them down for you. No, I'm not going to write them down. I'm going to show you this, sim.c. Sorry. Yeah, this is the structure which describes a variable node because this is a linked list in memory. So it's basically like six dwords. The first dword is a pointer to a name. Then there is the type. The type of whether it's, you know, an integer, a string, and as I later found out, is also the type, is it a function, because the functions are also on this list. Then an unknown. I think I figured out that it was something if data should be deallocated or should not be deallocated, something like that. But yeah, whether it was allocated from the heap or not, something like that, or whether it was in constant memory. Then there was the length if for a string, there was the length, and then there was the pointer to the data, in case of the functions, that was the pointer to the code to be executed, which was rather handy. And then there was the pointer to the next variable. Now, why did I put it in, you know, C file like this? It's actually quite interesting because when you compile it with debugging symbols, you can, then when debugging a binary, you can actually load this, the compiled file. So the compiled file in my case was called like simp0 in GDB, and you can use the variables then basically, the structures in GDB then. So what you did see me do is you did see me rename the GDB init before, right? So I'm going to actually show it to you now. What I do here is this thing. And this thing is actually, you know, run a shell command and compile this symbol. Gstabs is the option I needed to use to be able to GDB to actually have a structure in there, otherwise it was not compiled in. And then in GDB you just do add symbol file and the name of a file and the offset in memory of a file is located, but there's obviously no sections in this file, it's just a struct definition, so you can put 0, it doesn't matter. The rest of this is actually will be useful in the second exploit, so I'm going to ignore it for now. Okay, so given this, I was able to kind of debug it already. And I'm going to show you the variables in memory, but to do that, I need to set a breakpoint. The question is where am I going to set the breakpoint at? And I'm going to set the breakpoint probably here-ish is okay. Let me switch to assembly view. Yeah, I think here when you break in EAX you should be able to have here in EAX you should be able to have like a pointer to one of the variables, which is exactly what I'm looking at. I'm just wondering which one is it. Yeah, I think it's this here. If I break here in ECX, I should have a pointer to one of the variables, and since it's a linked list, I can just walk through the list. And I'm going to show you the variable then. So, okay, I do need to run GDB. Sorry. Okay, so first I'm going to add the symbol file, right? Okay, yes, I want to load it. Now I'm going to do the breakpoint, this address I did mention, and now I'm going to run it. It can be like any place in the file where you can just get a pointer to the variables. So I need a string, and now I need to index it, and this should trigger the breakpoint, which it does. And I did say ECX, right? So this is a heap address, I believe. So on this machine, as I said, there is no ASLR, so the heap range is basically what it is. It's pretty predictable. You can memorize these addresses, or the range at least, and not the addresses themselves. Okay, now I actually did have a comment which allowed me to list the variables, and I'm not going to retype it, I'm just going to copy paste it from my notes. As soon as I do find the notes, though. Okay, here it is. So, it's like this. While iter, first I need to, I think, set the iter to something. Yeah, so I'm going to set the iter first to whatever the value of ECX is, because this is where is the first variable, I believe. I can test it with doing like this. So struct, and it's called vnode pointer, and ECX has a pointer to the structure, and I'm going to dereference it. So yeah. So this displays me the name, which is a pointer, and it points to a name of a variable, which is a, which is correct, right? Because this is what I defined here. And then the length is 4, because ASDF is 4, right? So this is correct. And then the data is here, should be here. So if I do print char pointer to this address, it actually should display ASDF, which is correct also. And this is the pointer to the next struct node. So okay, so iter, which is an iterator, basically points to this, and now I can make a loop until iter is, you know, not null. It's just a standard walking through a linked list. Then I can do, for example, I think I had a couple of... I'm going to use this. Just like printing the name and the type. Maybe the length. Let's just keep it at that. And then I'm going to reset the iterator right to the next field. I can like use this pseudo C syntax. Okay. Oh, sorry. My bad here is actually that I didn't set the proper type for this, because this is actually struct node, vnode. Yeah, this is now correct. So while print then. Now I might not be printing from the beginning of a list, and it probably is referenced somewhere in like the global memory, but I don't really care about it too much. What I did notice is quite obvious, right? But at the beginning of a list there is the newest variable, which is okay. So yeah, so these are all the variables which are in memory. Now, A is the variable which we added, and it has the type 120, which is string. Then according to my notes, 11f is integer, 117 is actually a, and 119, and so on. These are actually functions with different amount of different types of arguments, and I think this is like one argument of whatever type. So yeah, so these are the name of the functions which are already there. Now, the kind of problem here is that like go away, it's probably exiting, right? But it's not. It's like added, it's probably something, but it's also not. Like all these names are like bogus, and we had to like reverse engineer each single one of these functions to be able to know what they do. Now, as I did mention before, the data field for the variables actually did point out to the code of that is supposed to be executed in case of functions. So, well, it was quite easy because we could like also display, you know, the code field here, the code pointer, and look in IDA what does it do. These were actually super simple. Now, we did find a bug, a new one, but I'm going to get to that bug in a second. And before I do that, I'm going to exploit the previous bug. Now, the previous bug, exploitation of a previous bug actually depends on one thing, which is knowing the heap layout. What I did end up doing is I basically hooked malloc and free to display the information on how much memory in what place is allocated. So let me show you the scripts which are responsible for that. I'm going to move my GDB init to be named .gdb init to be actually executed. So there are a set of two scripts. One is helper.py, which I'm going to show you in a moment, and then there are like these two, these three breaks. So if you do break something and then commands, then it allows you to script on what happens after this breakpoint is reached. And in my case is like, if that breakpoint is reached, silent means like don't display any messages apart from whatever prints you have in the commands, right? It just sets the last malloc to EAX, and EAX is, if I remember correctly, I might be misremembering, but this probably was the size of the allocation. Then there is probably the exit of malloc function, which runs the malloc helper with this, and it displays a message saying that at this address on the heap, these many bytes hexadecimal were allocated. So yeah, so last malloc, so this had to be the size of allocation. And this is actually hooking to for free, which does display the information of like, hey, like this block of memory was freed. Now free helper and malloc helper are actually Python scripts, which are in this helper.py file, which I'm going to show you as well. So this is probably the most important function in GDB scripting ever, which is like evaluating an expression as an integer. Yeah, it looks like this. It looks scary, but that's how it is. Yeah, you just like, it's boilerplate code, you just copy paste it. Now, there are just two commands here, like the malloc helper, which does, what does it do? It registers itself as a malloc helper command, and after that it maintains a map, like a dictionary, right? It's different here. It maintains a dictionary of addresses and sizes, and 3 goes the other way around. It deletes actually the address from the map, but it also displays how many bytes were freed at that region. We need to store it in some map, because it's, 3 doesn't have this information unless you dig into the heap heap fields, which I didn't want to do. Or like it says like it's actually not in malloc. Now, this script isn't foolproof. It actually like ignored some other functions which did allocation, and it was quite funny to hit this branch quite often, but that didn't matter. So that's it. You actually need to instantiate both classes at the end to be able to register the commands. Anyway, so when I run the binary with the script enable, it actually looks a little different. It asks me for some stuff, and I do run it, and it shows me all the allocations which are happening. Now, this is important because if I allocate one variable, right? Let me do it like this. And then when I allocate another variable, it shows me the addresses where the stuff were allocated. Now, what is what? Because you can see that per variable there are actually 3 allocations. I have absolutely no idea what is this allocation, the middle one. I don't care, it was not needed, I didn't have to know. For the first allocation, it was actually 18 bytes. As I did mention, the 6 D words, right, was the size of the variable vnode structure, which was a variable node, right, in the linked list. And 6 D words is actually like 0x18 bytes, so that's it. And so this is this vnode structure, and then there's this, which is kind of correlated to the size of a string, right? You can see this is probably 2 letters larger, this is D, this is B. So this is the data, this is the allocation, the pointer which is placed in the data. And having the addresses, I can actually, calculate the offset between the offset between my field, one variable and the other variable, and if I do negative indexing, I can overwrite the variable field of the previous variable. Therefore, I can change the type, for example, from string to code, right? Because that gives us like type 1. We could actually go for type 2 here as well. We can change the type to string, change the length to whatever is needed, and change the address to whatever is required by the judge binary, and go for type 2. But instead, I usually go for type 1. That being said, PPP usually went for type 2, and be sure to read the their write-ups, which is linked like in the description of a video if you're watching it later on, and which I did pass around on the channels before. They actually say why did they use type 2, and it was because it didn't crash the binary. And since it didn't crash the binary, then the teams didn't know what hit them. That was basically the idea behind it, which was really smart, I would say. Okay, so let's calculate the distance maybe, and let's do a quick exploit here. I'm probably not going to fully do an exploitation of the next bug, because the next bug is a heap-based buffer overflow, but I'm going to explain how the exploit works, which I'm going to show you. Anyway, so the addresses, right? I'm going to use Python, because why not? Let me whoa, I wanted to make this console smaller, but I ended up making it bigger. Okay, yeah. So welcome to Linux. On Linux, actually, if you change the size of a terminal, it generates a signal, right? And since it generated a signal, and the decree binaries don't have signals, there are no signals there. You did see the syscalls, 7 syscalls, right? They don't handle signals, so it crashed the binary. So I need to actually quit and rerun it, which is okay. The addresses are going to be the same anyway. Well, maybe not the same, because I'm actually putting a different amount of data probably here, but more or less the same. Okay, so again, I know that data of BBBBB is at this offset, right? Because this is the data. So I'm going to copy this offset. I'm going to call it just B. Perfect. I do need to do this though. Okay. Now, I know that the address, sorry, that the A is basically pasted here. The vnode structure of it. So I'm going to do this. Yeah. Now I'm going to just, you know, do a subtraction. Like no magic here at all. B minus A minus B. Actually, I need a negative value, and this is the offset to the beginning of the structure. Now, I probably should show you, or should show myself as well. I'm going to. I have the structure noted here again in my notes. So the type field was at offset +4. So it's going to be actually A minus B +4. This is the offset of the type field, and I do need to set it to 117. And this is already hexadecimal 117, so it's quite easy because I know I need to set it to like 17, 01, 00, right? So this is quite easy. I'm going to just do B first byte first because this is byte by byte, and I need to set it to. I can actually use escaping here, which is quite convenient. And the next byte, which is 7, obviously, because these are negative numbers. I don't need to change it. Actually, it's a 1 already there, so that's okay. And now add the offset of, according to my notes, do I have some secrets at the other side of this? No. That's good. It's +10 as in +16. So this is the offset of where I'm going to put my AAA, like for 1, for 1, for 1, for 1. This is what I'm aiming at in this demonstration. So again, it was 96. It's A, then 95. I need to, you know, place 4 bytes, like EIP is 32-bit. Okay, and now I'm going to actually run A as a function. Let me maybe put a meaningful value here, like 4242, because I do remember it ends up in the register. Yeah, and as you can see, we have EIP at for 1, for 1, for 1, for 1, and if I look at registers, I actually do have control of ESI, which is great, which is exactly what I need for type 1 exploitation. So yeah, this is how another vulnerability was exploited, which again I did get from the patch from PPP. Now the sad part is that everyone stole everyone's patches, and when I finished writing this exploit, it was like super quick. It's super easy, right? I already knew the structure of vnode anyway at this point, so everyone was patched. So we didn't get any points from exploiting this vulnerability, so that was unfortunate. Okay, and the last vulnerability I wanted to show you today is in the function which was called new1, I believe. Let me maybe, I have in my notes the address of a function new1 in IDA. We actually went through all the functions and noted whether it's vulnerable or not. And there were some like things which crashed due to integer overflow, but we couldn't really. I don't have a symbol. But we couldn't really exploit it, so we decided not to even patch it. Okay. Yeah, this is the new one. Now, it might look a little scary, but what it does, it checks if both, or it actually takes 3 arguments, and I believe all of these arguments are required to have the same type, and the type is supposed to be 120, which is a string. Now, what it does, it changes a given string to a given substring to a different string. I'm going to actually show it to you because it's easier. But it's like a standard string replace basically thing. give or take standard. Yeah, so let's do it like this, and then I'm going to do a new one. I don't remember the order of arguments. I think it was like this: first the needle, and then what we change it to. And we change, let's assume we change to YYY. Yeah. It returns the value, I believe. I'm going to output this, and A, as you can see now, has the YYY instead of X here. So it's like a string replace. And it'll do it to actually every X it found. But only in the original string, so there was no recursion here, like no string recursion, string replace recursion. Now, you might expect a bug here like an expand tab, which is like miscalculation of the destination buffer. And that's true, but there were actually a couple of checks against it, and the problem was that there was an integer overflow, and it was somewhere here, I believe. Yeah, there was like actually here, I think here there was a problem with integer overflow, meaning one of these was the amount of a substring occurring in the base string, right? So for example, how many x's were there? And the second one was actually the size of the destination of the string you want to put in place of x. Now, in this example, it was, for example, 1, right, and 3. So that's simple. But what you had to do to exploit it, you had to get, for example, 256 x's and replace it with a string which is, for example, 16 megabyte long. I don't remember the exact values, but the idea was to overflow it. And after you overflow it, you get a rather small value here. And once you get a small value here, well, it is being copied later on to the input buffer. Like the string is going to be, the original string is going to be copied, and then parts of it, of course, and then the substrings are going to be replaced with the destination strings. Which means it will overflow, but you know, if it overflows by 4 gigabytes, this is not what you want to achieve. You want it to actually end, and it was quite possible to overflow the memory area where, which check was it? I think there was a check somewhere here, maybe somewhere around here, but it did take from the from memory, basically from heap memory, it did take the amount, and if the amount was like smaller than something, then it actually did exit the loop early. So you had to, with the heap-based buffer overflow, override this variable, so this loop would exit early, and then it would go to a mem copy. But since you could also override this length on the heap as well, you could put 0 here, so this wouldn't mess up your crash your process basically, and then do it exit. And after the exit, what you're aiming at is you're aiming at changing again the type of another variable, and basically changing the the destination, the data pointer, which was the code code function pointer basically for function type. So how did an exploit for that look like? I'm not going to create an exploit offhand because, well, I'm not sure I could do it in 15 remaining minutes of the stream. It took me a couple of hours to craft this exploit, well, including all the scripting for GDB I did. But it looked like this. So B was basically what was the string which was replacing what was this? What was the string that replaced the X, the substring which we are looking for? Now, I actually did replace the letter A. Sorry, is that accurate? No, I did replace the letter X, but it was a small x. And as you can see, this base variable I created, I used another function added, which actually concatenated to strings, and this grows. This is like 16 bytes, and this makes it twice as large, which is 32 bytes, twice as large 64, 128, 256, 512, 1024. 2K, 4K, 8K, 16K, 32K, 64K, 128K, 256K, 512K, 1 megabyte, 2 megabytes, 3 megabytes, 4 megabytes, 5 megabytes, no, wait. 1 megabyte, 2 megabyte, 4 megabytes, 8 megabytes, and then it added C, and C, I believe, was only 1x. So at this point, at the end here, right, we already had an overflow, and if you multiplied the length of B with amount of x's, you get 0. Because, well, it overflows, right? So it's actually like 4 gigabytes, but 4 gigabytes in a 32-bit binary doesn't fit, and it fits only the zeros at the end fit. So this is a 0, but we will add 1 more. So this 1 more is actually multiplied by the length of B. The length of B is, well, there is some escaping here, but it was, I don't remember correctly, it was around 300, 256, something like that. So yeah, so you overflow and you override with whatever is in B. Now, as you can see, there is actually a structure to the B variable. Wasn't there a help function in the challenge? No, there is no help function. No, I didn't check. It would be so funny if I would like to type help now and it would display me all the functions. But no. Thankfully, no, because I would feel really stupid. Anyway. So B was structured basically similar to the trick I did describe earlier, like 4 bytes, and actually I do have an identifier here because there were this buffer was longer than there are letters in the alphabet. Okay, so there's a question: do you use tools like Pawn tools, Radar, PEDA? I actually did use PEDA, but it didn't play well with my script, so I disabled it in the end. I don't use Radar 2. I do need to spend some time, well, getting the hang of it, because, you know, the entry level of Radar 2 is, it's not like Binary Ninja or IDA. It's just, I have absolutely no idea how to use it. I mean, I know I've been doing reverse engineering for like 10 years, over 10 years, and I have no idea how to use Radar 2. I need to read the manual probably for it. Pawn tools, I don't. I know they're like a great set of tools. I have some my own scripts which I tend to use. So usually it's like my own sets of tools plus vanilla Python, vanilla GDB with some scripting. That's usually what I use. But I do recommend Pawn tools and the other stuff as well, which you did mention. Anyway, so yeah, again, quadruples basically with the identifier, and then when I already knew what is overwriting what I already had the overwrite and I knew what is overwriting what, and by looking in GDB, by inspecting the memory, I did replace some quadruples with some other stuff. Now, what is important here? Let me think. This is the type. I'm changing a type of a variable to 117, which again, as I did say before and as you did see before, is the type function, the function type. I don't remember what it is. We're probably going to see it. Yeah, I think it was the EIP. Yeah, this was the EIP, and it was in the POV, it was changed to EIP actually here. So this is what I was overwriting the memory with, right? Now I have some other variables which are called v0, v1, v2, v3, and so on. And each of them is actually is a string variable which points to data like this. Each of these actually copies this data. Now the size of this is actually similar to the size of B, and this is because I needed when it overflowed, right? And when this malloc happened here, where's the malloc? Is here. Sorry. When this happened, I needed it to allocate in the same region of memory, basically. So how did I do that? Well, first thing, they needed to be a similar size. Second of all, I needed to have some variables, and then I needed to deallocate one. How did I deallocate one? That was quite easy, actually, and it's done, I think, at the end. Because if you look at this function really close, you can see 3 here. And 3 does the allocation, obviously. So what this does is it just deallocates the data, not the vnode structure, but the data for v0. So it makes a spot in the heap, which is exactly by accident, by pure accident, not really. It's exactly the size of this, so this malloc is actually going to allocate in the same the place for this variable in the exact same spot where this 3 in the previous calling to the new one 3 did, right? This is what I needed, and the v3 was actually, as you can see, was allocated here. So if I do run, when I'm going to run this exploit, you're going to see that these comments don't do anything. These are just comments, but I can find in my output of GDB what address does it have and align everything properly. So yeah, so AAA was also, because I needed again to modify like this argument and this argument for the second call of new one, I did need my A variable to be actually after the variable which I'm going to overwrite. So actually, due to this placement of the O3 here, this is what's going to be overwritten. The A variable structures and the, obviously not the data, because the data at this point is like super huge and it's in some other parts of heap. But yeah, and v4, which I'm going to use for execution. So the overflow happens here, and everything is overwritten. Now what is infinity? There is no function called infinity here, but when I actually, what I do is I change this v4 to, I completely redefine this. And the name is, I think where is the name? This is the name. And when we look at it, so this is 08, this is probably 10. I have absolutely no idea what code W has. Let's check it. '86, but I needed hexadecimal. Okay, so it's 08, OA, then 57 before. If we look at this address in IDA, then we find a string infinity. So let's do the code. Yeah, so this is, I just defined a new structure for a variable basically, which is named infinity, and it's a function type with 117 actually says that it's a function type, and the code is located at AAA. And then I just call it. It also doesn't point, I think the zeros here, yeah, the zeros here are actually the next pointer. And I didn't want to point at any other variables which are on the list. I basically killed the list at this point because I knew they were corrupted, because this is a heap overflow. I mess up the heap quite a lot. So if the program would start looking through the variable list, it would basically crash. So in the end, there's like only one variable on the list, and that's infinity. This is also the reason why v4 was added as the last variable, because as I did mention before, the last variable was at the beginning of the list. So I was sure there was nothing else on the list at that point. Okay, so let me maybe show you the exploit that it actually works. Okay, let's run it. Actually, I'm going to write this exploit to some file. And GDB legit 7. Okay. Let's zoom it. It's going to start by spamming with, a lot of messages about allocations. But yeah. In the end, it did call the infinity, and we are again EIP is equal to AAA. And ESI is equal to 42424242, which happens to be exactly this. Exactly is the same value, but yeah, it's here even. So basically, yes, this is how the heap-based buffer overflow looked like in case of this binary. It actually, I think we were owning quite a lot of teams when we started this exploit. Then it fell down quite dramatically, but I think we were owning still 2 teams until the end of the competition, so we were quite happy about that, and this exploit actually getting quite a lot of attack points for us. Yeah, so this is actually everything I wanted to show you today. If you have any questions around this or around general CTFing, I still have about 5 minutes of my stream left, so ask them either on IRC or on YouTube channel. And apart from that, that's actually it for today. So thank you for being here and for watching. Do you have any questions I could answer? I know there's like at least a 10-second delay for the stream, so yeah. So I guess I'm going to see any questions in a second, if there are any. Okay, so while waiting for questions, do I have any fun things I can still show you? KrzaQ, actually a question. Do you think CGC-compatible CTFs will be a thing in the future, or will this be irrelevant now after the competition? It's actually a good question. My personal preference as a CTF player lies not in the CGC format, mostly because it there's no shellcoding part at all, and there's no, like, the second half of exploitation where you actually control the EAP, but you don't have your shellcode nowhere in memory, and you struggle with, doing a ROP chain. That's actually fun, and I like it. And CGC doesn't have it, so as a CTF player, I would prefer to have it. This is where our team is rather strong at, so I'm kind of biased here. But yeah, so I hope it's not going to be a lot of CGC format in the future. I do hope also that DEF CON goes back to the crazy platforms they had, like both a year ago and 2 years ago. It was fun to play CGC this year. It was great to see something experimental, something new. I just hope it stays at that, at being experimental, and we go back to the old stuff. Old stuff meaning actually, the daily stuff I interact with, and the daily stuff which security cares about, and not some experimental platform. Yeah. So that's my opinion, but the question was, do I think it will be a thing for CTFs? Let's see. For now, I think 3 CTFs had challenges with CGC. That's DEF CON Quals, DEF CON Finals, and I believe there was another one. I don't remember which one though, but there was one as well. Yeah. Okay, so there's a comment that from Jeremy that sounds like next year it might be experimental as well, because they mentioned, the organizers of DEF CON mentioned, and custom architecture. Custom architecture might be interesting as well. I would prefer like real life architectures though, personally, x86, ARM, MIPS, whatnot, like be it Spark, be it Titanium, but like real life ones. Okay, another question. Do you often fuzz to find the crashes in harder CTF challenges, or is most of it statistical analysis or educated guesses when playing with it by hand? So we do use fuzzing during CTFs, but it's like 10% basically of vulnerabilities we discover during CTFs are done by fuzzing. Maybe, yeah, it's around that, maybe 15%. Most of them we actually find by hand by analyzing. I don't believe we have a good method for analyzing stuff. So depending on the challenge, we actually sometimes do it like this. That was the most effective way, by the way, is that a couple of guys reverse engineer a challenge. Usually it's me, sometimes it's Redford. Redford is our reverse engineering specialist, basically. And then we pass it to Juru, to Mateusz Jurczyk, and he just comes and like, bug here, exploitable. And then he gets EIP to 41414141 and passes to me because I'm pretty good with shellcoding and I have some cool scripts for ROP, so I finish it, and that's usually the way we do it. So we have a machine called Juru which finds vulnerabilities for us. That's how we do it. Okay. I guess I'm going to wait like 1 more minute for questions, and if there are none, then I'm going to call it a day, call it a stream. I guess I can start by closing some windows. Okay, cool. So thanks everyone for joining. Thank you again to KrzaQ for being here, for moderating for me, and that's it. See you probably next week for another stream. I don't know the topic yet, but there will be some challenges that I will solve from CTFs, because I guess all my streams are going to be about security and hacking and CTFs and stuff like that. So thank you very much. Please leave your feedback either on the channel or pass it to me using email, on Reddit, or in the comments down below on YouTube if you're watching this after it was published. So thank you, and have a great evening, everyone. See you. I'm going to leave you with some music.